Hi and welcome to this specialist math topic, vectors and lines, Unit 3, Topic 2, Video 2. There we go. So this is going to be just a follow on from the last video, and I'm going to talk a little bit about the different forms of vectors representations of lines. So lines can be described as vectors in either Cartesian form, which is not as vectors, I apologize, or vector form or parametric form. Now, parametric form typically is the one you probably have seen the least, but it's also the in-between vector and Cartesian form. It's Cartesian form on the other hand, is the form you're very used to for representing a line in 2 dimensions, and vector form you will have seen last video. So that's where we have RT being our position on a line, A is the starting point, D is the direction, and T is the parameter. If you write something in parametric form, it means you're going to represent each of our variables, x and y, in terms of that parameter, which is t in this case. So we're finding a way to break down that x and y. And so you'll notice here that we break the a into a1, a2, and d into d1, d2. Let's have a look at this breakdown. So in vector form, here, if we have r equals a plus td, the vectors, well then r equals a1, a2 plus t, d1, d2, breaking it down into its 2-dimensional components. And therefore x and y equals this breakdown. We've multiplied the t into our directional variable. And we actually end up with kind of 2 linear functions for x and y, and they vary together. So x is changing as per time, y is changing as per time, and it creates this linear function. And of course, we can equate the top line, so the x and the y lines, and it gives us either this representation, x in terms of t, or this representation, t in terms of x. They're just rearrangements of each other, and y and t form the same similar relationships. It's actually from here, particularly at this stage, where we can cancel out t, our parameter, getting a function that is x in terms of y, and that brings us back to Cartesian form. So it's important to recognize that this parametric form is kind of the in-between. Very similar results for 3 dimensions as well. Lines can be described Cartesian, vector, or parametric. Cartesian exists, but it's a lot harder to write a line in Cartesian form in 3 dimensions. So we really are using vector form a lot more, and that's why we introduced this form. And of course, parametric form still works. We just end up with an A3 and D3. But it's now we get to a point here, if we want to go back to that Cartesian form, t equals this in terms of x, t equals this in terms of y, and t equals this in terms of z, which in Cartesian form means that you end up with x minus a1 over d1 equals y minus a2 over d2, which equals z minus a3 over d3. And because it's 3 dimensions, we could now cut one of those equations and look at how x varies in terms of y or y varies in terms of x, but then we wouldn't be considering the 3rd dimension. So it does get a lot harder to visualize that Cartesian form. We tend to stick with the vector or parametric form here, probably the vector form. So let's have a look at example 4 from this series of videos, and I'll just talk to how to do this one quickly, and then we're done for this little subtopic. So the line L can be described by the vector r equals, now remember, this is our A, and this, it's 2 components, but we're missing a j component, which doesn't mean it's missing, it means it's 0j. This is our direction vector. So we've got our direction and our A. Determine the parametric form of L. So hopefully, seeing what we've seen, this is reasonably trivial now. We get r of lambda is equal to, I'm going to put them down as vertical vectors here, or column vectors. I get 2, 3, negative 1 plus lambda 3, 0, negative 2. That 0 is massively important to make sure you get it in the right place. And of course, r lambda can now be written as x, y, z is equal to 2 plus 3 lambda, and then 3, and then negative 1 minus 2 lambda. And so, of course, this means that x is equal to 2 plus 3 lambda. Y is just always equal to 3, and z is equal to -1 minus 2 lambda. Now we could rearrange this to get lambda by itself, and we could actually get a function x in terms of z because y doesn't vary. So we could get a Cartesian equation of x in terms of z, and this whole linear function, if I draw this in 3 dimensions, which is quite hard to draw and quite hard to visualize, but if this is x, this is z, and this is my y-axis here, well, y equals 3 here, and we produce kind of a plane at y equals 3, which I'll do in a different color. So the plane is kind of this. It's like a piece of paper that's standing up that's cutting the axes at y equals 3. And our linear function is entirely on that plane because y always equals 3. And so using that plane as an xz axis, we could describe this in Cartesian form nicely, but we're not going to go to that level. For now, they're parametric form, which is what the question's asked. All the best.